2z. So the order of zeta 3 squared and 1 plus 2z is equal to 6. Finally, let's do one more example. Now this looks actually quite difficult, right? But it is difficult. I mean, it's not difficult. It just looks quite like it requires a lot of time. But it only does require a lot of time until you actually start noticing some things. So let's look at the group G equal to z mod 4z cross z mod 6z. And let's look at this element. 1 plus 4z, 2 plus 6. I want to know its order. Now the operation is addition on both coordinates. Here it's the addition of congruence classes mod 4. Here it is the addition of congruence classes mod 6. So I need to keep adding it until I get the identity, which is 0, 0. In other words, until I get 4z, 6z. How many times do I need to add it to itself? Let's just think about it. Okay, if I add it to itself twice, let's just first focus on the first coordinate. If I add this to itself, I get 2 plus 4z. Doesn't matter what I have here. This isn't the identity because I must have 4z on the first coordinate to get the identity. So how many times do I need to add this to itself to get identity on the first coordinate? I need to do it 4 times, right? So 1 plus 4z plus 1 plus 4z plus 1 plus 4z plus 1 plus 4z. 4 times this element must show up so that on the first coordinate I get 4z. And in order to get the identity, I must have 4z on the first coordinate. Okay, if this still doesn't give me the identity on the second coordinate, then I have to keep adding. But if I add this element 5 times, I don't get the identity on the first coordinate. The next chance for me to get identity on the first coordinate is if I add it 8 times, right? Because 4 times that gives me 4z. 8 times that gives me, well, 8 plus 4z, so 4z, and so on. So because to get 4z on the first coordinate, I need to do n times 1 plus 4z with n divisible by 4. Right? If n is not divisible by 4, I don't get 4z here. So to get 4z on the first coordinate, I need to do n times this, where n is divisible by 4. So the only candidates that I can get the identity here is the multiples of 4. So the order of this is divisible by 4. Again, right, the reason is if I do it 3 times, then I'm going to get 3 plus 4z on the first coordinate. That is not 0 on the first coordinate. The only way to get 0 on the first coordinate, if I add it 4 times or 8 times or 12 times. Okay, so the order must be divisible by 4. But similarly, to get identity on the second coordinate, how many times do I need to add this to itself? This thing, right? So 2 times 2 plus 6z, that's 4 plus 6z. And 3 times 2 plus 6z, well, that is 6 plus 6z, so that is 6z. So I need to add this to itself 3 times or 6 times or 9 times. So in order to have the identity on the second coordinate, this needs to be added to itself a multiple of 3 times. So similarly, to get 3z on the second coordinate, sorry, 6z on the second coordinate, I need to do m times 1 plus m plus 2 plus 6z, m times 2 plus 6z, with m divisible by 3. So the order is divisible by 3. So this saves me a lot of work, because I know the order is divisible by 4 and by 3. So no point in checking 7 or 9. What's the smallest number for me that makes sense for me to check? The smallest number that's divisible both by 4 and by 3, that's 12. So So 12 must divide the order. Let's check. And if I do that, so because it's addition on both coordinates, we sort of said that we're going to put the 12 here rather than there. So that is 12 plus 4z, 12 plus 6z. Oh, but that's 4z, and that is 6z. So I did get the identity. So I know that the order of 1 plus 4z, 2 plus 6z is 12. So you can apply this principle to other situations. So let's look at last example. Mu 5 cross z mod 7z. Multiplication here, addition here. And so I want to know the order of zeta 5 squared 4 plus 7z. So zeta 5 is cosine 2 pi over 5 plus I sine 2 pi over 5. So how many times do I need to, so to what power do I need to raise zeta 5 squared to get to the identity? The smallest positive one is going to be, so equal to 1, smallest positive n is 5. We did the example of just the group mu 5, so you know it's the order of mu 5 squared inside just mu 5 is actually 5. So the smallest possible integer, positive integer is going to work here is 5. What about 4 plus 7z? So you can check that the order of 4 plus 7z is 7 in z mod 7z. So the smallest positive integer that works for 4 plus 7z is 7. So the order of this is divisible by 5 and 7. So 5 and 7. So 5 divides the order. And 7 divides the order. So the smallest number that it makes sense to check is 35. And in fact, let's check that. To the power 35. Well, that's zeta 5 to the 70. And 35 times 4 is 140. Plus 7z. Remember, here I'm using multiplication, here I'm using addition. So this I'm raising to the power 35, here I'm multiplying this by 35. Oh, this is clearly the identity. This is 1, 7z. So the order really is 35. So doing this sort of analysis, you can arrive at an order of an element in the direct product of groups quite quickly.